Welcome to the OrionX Download. This is a podcast where we discuss and simplify the big ideas in technology that are changing the world. Hello everyone, welcome again to the OrionX Download podcast. I'm Shaheen Khan, and today we're taking a look at the semiconductor industry and how a certain university project has gathered steam and is disrupting the market. Let me set the scene here. Every chip has an instruction set, the language that it uses to process data. Over the years, several such instruction sets have been established. Each of them is controlled and governed by their respective owner, usually a very large company. RISC-V is an open source approach to chips. Open source has really changed the software business, but it's been harder to apply to hardware. RISC-V seems to have cracked the code. Initially created at the University of California at Berkeley, RISC-V has grown over the past 10 years to a position of pretty serious prominence. It is clear that it will remain important in the coming decades. Here to discuss this in more detail with us is my guest, Mark Himmelstein, who recently joined RISC-V as Chief Technology Officer. Mark and I worked together at Sun Microsystems some years ago, so it's a pleasure to reconnect with him and to get his perspective. So with that, let's go to our conversation. Hey Mark, great to have you here. Thanks for making the time.
My pleasure. Good to speak to you again.
So RISC-V, as I was saying in the preamble, is obviously a big deal, and I was so delighted a few months ago when I saw the announcement that you are the CTO for the company. Now, you and I worked at Sun Microsystems together many years ago. You were changing the world in big ways then, and you went on to do a bunch of other really cool stuff. But for our audience, please give us a little bit of your background and how you ended up at RISC-V.
Absolutely. Thank you, Shaheen. So there's probably three major pieces of my background that led me here. The first is that I was employee 45 at MIPS. So in the 1980s, when Dave Patterson was doing RISC-1, it eventually ended up as Spark, and other RISC processors were starting out. So the predecessor to Alpha, I was at MIPS. So we were changing the world back then and making people think more about compilers and optimizers and memory systems and instruction sets. So I spent a long time there and got a great grounding in learning about architectures and ISAs. And eventually I ended up at Sun Microsystems with you running the Solaris team. And so I ran the Solaris team for about 5 years, helped start ZFS, D-Trace zones, and a bunch of other what I would consider to be innovative pieces of Solaris that occurred around the year 2000. And eventually I ended up starting a company that was a massively parallel flash-based compute engine targeted at big data, and sold that off to EMC in 2015. But in the intervening time, I worked everywhere from the ISA all the way up to applications. So things like financial software or other system software, operating systems, hypervisors, so on and so forth. And so I have this fairly broad perspective.
You do.
On architecture. And that was very interesting to the folks involved with RISC-V. And if you couple that along with sort of the massive coordinational work that it took to guide Solaris into its releases and its significant impact on the industry, I had to coordinate the work of a lot of people that weren't necessarily working for me. And so that combination of skills made it interesting. But in the end, interestingly enough, it was my MIPS colleagues that threw my hat in the ring. I really wasn't looking for anything. And they said, hey, would you be interested in this? And I said, sure. And so they threw my hat in the ring, and me along with another 30 people. And so I ended up with the position, and I was very excited about that. So for me, the traction was that it was very tech-centric, very technology-heavy, but also had the same kind of flavor as this changing the world at MIPS or at Sun or at Graphite Systems with the compute engine. And so for me, that's very attractive, that combination. And also, I have some organizational skills.
Yes, you do.
And bringing that along really helped me come into the RISC-V world and help them.
I want to applaud your MIPS friends to have thrown your hat in the ring, because truth is that there are so few people who have as broad an experience as you do, touching every part of the stack as intimately as you have. So that's really nice. Well, great. So RISC-V.
RISC-V started in Berkeley, and it's just had its 10th anniversary, 10th birthday.
Wow.
And that's very exciting. It is intended to be a very extensible, flexible architecture that's going to last a long time. Berkeley folks did RISC-1 through 5, and this is the one that's intended to last 50 years. So it's a very exciting time, and it's really a very interesting time in history. So we get the benefit of history looking at all the things that came before us from the RISC and the CISC world, all the MIPS and Sparks and Alphas and HPPAs and Powers, et cetera, that have come before us, as well as x86 and ARM. And so we get to learn a lot from those things and benefit from them and provide an incredible opportunity ISA product to the world that is the first chip of this magnitude that really has its origins in open source.
Right.
And so if you go back and think about Linux in 1990, people would have said, hey, the operating system I'm going to pick is going to be AIX or System 5 or HPUX. And Linux wasn't even an afterthought. And over time, what happened was the power of the community and the pride of ownership of the developers and the continuous improvement that has occurred over the last 30 years has made it a no-brainer in the year 2020. We expect RISC-V to be the same thing. In 10 years, it won't take us 30 because we get the benefit from Linux, leading the way, and folks like Apache and Hadoop and, even Eclipse.
Yeah, definitely.
Laying the groundwork.
There's enough changing. Yeah.
Yeah. So we expect that in 10 years, we are going to be in the same position where people are going to say, hey, that's the right thing. And we're just beginning now. We're still finishing all the extensions. People are doing implementations. You're going to see a proliferation of devices in products over the next 2 to 5 years that are going to put the number of deployed RISC-V cores in the hundreds of thousands. So we are very confident that we can do that. And again, this is a community effort. So there's a pride of ownership and a feeling like they did it. But also, it provides the same kind of benefits as Linux with its licensing and royalty structures, which is free.
Right. You mentioned there was a RISC-1, 2, 3, 4, and this is the fifth iteration, and it came out of Berkeley. What do you think changed that made the timing so appropriate for this to happen? I mean, this is not the first time that chips have tried to go open source or have tried to go standard. We were both at Sun Micro, and Spark was even an IEEE standard, and Spark International was pretty easy to license. Or, they were trying to do some similar things. But then you fast forward to today, and RISC-V seems to be at the right place at the right time and really building a big community behind it. What would you attribute that to?
Well, it's one of those perfect storm things. I think that, number one, we can't underestimate the rapid development capability that exists today to go ahead and create a new chip. We just recently had one of the universities had 4 undergraduates create a RISC-V chip. They were undergraduates in 4 months with less than $10,000.
Wow.
And so that just gives you an inkling of how rapidly you could develop a chip, a product based on RISC-V, whereas you and I know that 30 years ago, that was $100 million and 100 people, right?
Exactly.
So that's one piece. I think the second piece is something I spoke about before, which is we have the benefit of history. We just learned a lot over the last 40, 50 years that we were able to take advantage of and say, hey, if you're at this piece of history, you need this and this and this, and you have the opportunity to excel and innovate here. So that was really important. I think the other piece was very much that this was a community effort. So there was great interest in people being able to do what they wanted to do, when they wanted to do it, and still benefit from the community doing a lot of the heavy lifting for the stuff that had to be done no matter what implementation you were doing. And then finally, I think over a period of time, people learned from the Linux world. I mean, look, the license fees and the control issues around things, whether it be Spark and MIPS and Power that all have open things, they got put into the open source world. They still had an 800-pound gorilla behind them, guiding them and pushing them and so on and so forth. And the software pieces had similar things. They've all kind of moved to Linux. But if you really want to buy an IBM Power-based machine running AIX, you can still do that, and you pay a significant premium for that. And these guys have done a great job. We don't think that in today's world it's which one, it's how many and how well. And we know that there's a bunch of companies that are multi-denominational and either for evolutionary and historical reasons have other ISAs or because they feel like one's more appropriate for one thing and another for another thing. The licensing and the royalty structure with the proprietary chips played the same role in the decision making of corporations that Linux did with respect to the proprietary operating systems. And so that came to a head in 2015, 2016. And that's when, 2015 is when the RISC-V Foundation came into being.
Right.
And I think it was that set of events and opportunities that led us to get this kicked off and led us to a point where we could be successful. And now we're in the sort of the explosion mode that you have when people go, okay, I've got this great technology. Let's figure out all the ways we can use it and make money on it, selling it to our customers.
Right. Definitely a different business model. Now, when you say open, it's great because there's flexibility, there's freedom, there's community, but then the diversity that you try to encourage can also lead to incompatibility and inconsistency. So how do you rein that in such that the community doesn't splinter off in too many different directions?
That's a great question. And it is something that is really critical because we've seen other architectures in the past diverge in so many different directions that some of the standard distros, for example, said, go away until you clean this up because we can't go to 20 different variations, right? So we know that from the beginning. And so what we've done is we've laid down, look, this basic stuff, the arithmetic units, load store and branches and all those kind of things, those basic pieces constitute what we call them profiles, a base profile that coupled with ABIs and all the other things that go into a target of where you're going to run software on and applications on and operating systems and hypervisors on, is clear that if you're going to support this, you're going to be able to run the same applications as other implementation.
Mm-hmm.
The same thing's true on the operating system level. So we have both a privileged spec, which is the operating system standards, and we have the unprivileged spec, which is basically the application standards. And for each one of those, we have this concept of a base profile that if you go towards this base profile, you'll inherit the ability to run the same applications between companies.
Uh-huh.
And of course, you have to pass all the things. I mean, you have to do your own DV and you got to pass, compatible compliance tests and ABI tests and application tests and benchmarks and all the things that you do in order to put out a system and verify that you are compatible with what's out there. But we get to go to the distros and say, you don't have to go to 100 different variations, just go to these 2 or these 3.
Uh-huh.
And you are going to satisfy the basic needs of the community. Now, what does that do for somebody who wants to innovate? Well, they can innovate in a number of different ways. One is they can take that base thing and innovate, for example, in the direction of performance.
Mm-hmm. Mm-hmm.
Huge number of cores and memory interconnects and I/O subsystems or power consumption or, whatever it is they want to innovate in. And they could just stay with the base stuff and be very successful. Or they can go ahead and create what we call a derived profile, which is inheriting all the base stuff, but adding some special secret sauce, the proprietary instructions that help them in their applications and in their target marketplaces. But because the derived profile totally inherits the base profile,
Mm-hmm.
it's like if you think about C++ or Java inheritance,
Right.
This is like inheritance without overriding. You inherit the ability to go ahead again and piggyback and run the same applications and the same system software as you do in other implementations. And then finally, if people want to go ahead and do their own thing, they can. We allow for custom profiles and people can go ahead and do kind of whatever they want. They can do things earlier than the standard's ready. They can, have their own private version of things. They could have some new thing and it's all fine. But they know if they go into that, they have to go ahead and work on the whole ecosystem to make that piece work. The tool chain, the operating system ports, the applications, and so on and so forth. And people are doing all 3 of these. They're doing just the base stuff, they're doing derived stuff,
Mm-hmm.
and they're doing custom stuff. And that's how we both provide a way to not have too many variations and to really leverage between implementations, between companies, between customers, but still allow people to innovate either in the implementation of the base profile, or by adding extra things in a derived profile, or doing custom things in a custom profile.
That's right. I suspect some of the stuff you're talking about is exactly what's gone through risk 1, 2, 3, 4 until we got to 5. It was to iron out wrinkles like this.
I think that it's a stronger statement than that, actually, Shaheen. I don't think we understood the problem way back then. I think it actually took our friends, all the other chip companies, RISC and CISC, to run into these issues, especially when you start talking about applying it to Linux or to LLVM or to other things, that you start running into this variation problem. And then they consolidated and figured out how to make it easier for the distros to support a future set of things on an ISA. Again, we stand on the shoulders of giants and get the benefit of history so that we can go ahead and not have that issue right out of the
That's a very good way of putting it.
Yeah.
Now, RISC-V is a rapidly growing community. Every time I check, it's been growing quite nicely. So what is the current status? How big a tent are we talking about right now?
We certainly can talk about like the number of members. I think, the last I checked, even between the time I joined and now, it's
right.
grown. It's grown about 10%. I think we're about 680 at the moment. We have this incredible get together in September called the RISC-V Global Forum. And a bunch of those people are coming together to share their technologies and things that they're doing, some things that we're doing as a community. And those people are also producing products. So there's probably, we don't know all the details because some of the stuff is stealth and proprietary and private. But we think there's like 100 to 120 discrete different products that are going to customers, not including university projects or research projects that are going to customers over the next 2 to 5 years. And people are working on that stuff. We believe there's about 1,000 people involved with the community that's actually defining the ISA and the ecosystem actively. And that does not include other organizations that exist in the world to do things like CHIPS Alliance or Open Hardware or Low Risk that are concentrating on other pieces. We concentrate very heavily on the implementation independent components of both the ISA and the ecosystem. And then we support and enable and encourage all those other pieces to do more of the discrete, specific sharing that companies want to do. Some companies want to do, because think about it. If you're going ahead and concentrating very heavily on a low powered part, why do you want to go ahead and spend your time writing compliance tests for the ISA? You don't, right? Why do you want to spend your time even doing the design for the chip or the DV for the chip? Because a lot of that can be shared, and then you can go ahead and modify the pieces you need to in order to make sure that you fit the power envelope. So those folks are really able to take advantage of some of these other organizations and piggyback on them, and then innovate where they really add value. And I think this is the promise of open source, whether it be software or hardware, is that there's common denominator stuff that you have to do no matter what implementation it is. And you get the benefit of the community working on those pieces and not replicating them. We're optimizing the spend of money globally on technology by allowing different implementations to share technology and be egalitarian about it, but also fuel innovation.
Well, the governance of this, like you just alluded to, is really quite interesting all by itself, because removing duplication is always a good thing. But then to manage to do it across multiple organizations is really the innovation. Now, with such a big tent, maybe we can go around and look at some big megatrends in the market and see what the community is doing in favor of each one, because I think it's important to put the expansiveness of the vision and what is becoming reality and talk a little bit about that. So the way we look at the future within OrionX is IoT is the fountain of data. That data gets communicated through communication channels, increasingly 5G. In order to make sense of the data, you have to look at AI and HPC to interpret it and find meaning in it. And then you want to accelerate those applications. We've seen the reemergence of vector computing, matrix computing, tensor computing, different kinds of parallelism, whether it's GPU type or FPGA type, et cetera, fabric, memory, HBM, all of that. And then you also see some new transactional methods in terms of blockchain and immutability and things like that. So let's go through them one by one and maybe get your perspective on how RISC-V can not just disrupt, but add value and innovate in each one. So let's start with IoT. I imagine that's an area that RISC-V would be very strong in because you're looking at sensors and microcontrollers and the ability to really customize.
It may be a broader thing that includes IoT and other things.
Hmm.
I think there's a whole realm, which we sometimes allude to as embedded, that crosses IoT and computers that are showing up in
Hmm.
devices like disk drives and so on and so forth, and in bigger commercial products like automobiles.
Right.
And so these are things that are not general purpose compute appliances. What they are is that there are specific targeted appliances that people use a processor to do stuff that they might have done with discrete logic not too long ago,
Hmm.
right? And so you can see whether it be a graphics board or a disk drive or your favorite microwave or toaster or something that sits even in a some kind of 5G cell or something like that, where people in the past have gone ahead and used other IP for other ISAs in order to incorporate it. Now a lot of those people are taking a look at RISC-V. And the reason is, again, the royalty structure is great and the freedom is even greater. And so you might see graphics controllers out there with 50 different cores doing 50 different things on them and other processors on the same board. I mean, again, it's this world now where people use the best thing for them at the time. And we're very happy about that. We think it's great. And so this piece of the world is really wonderful. And we have a bunch of people who are involved with us in helping that piece of the world. Now, I can just give you one sort of general set of groupings of things that we're doing to support all these worlds.
Hmm.
And that is we're looking at code size reduction because we know that size in that piece of the world is really hard. We want the chips to be smaller. And truth is, code size translates almost perfectly to power reduction. And that's important in that piece of the world as well.
Hmm.
And so we have great efforts, everything from different sized instructions. We support 16, 32, 48, 64. Sometimes you might see an embedded want to use 48 so that they have a good immediate instruction or something in there. But most of the time they're interested in 16s.
Hmm.
But we also have ZFINX, which is basically doing floating point out of integer registers. So you don't need to spend all this logic to have floating point registers out there and another
Right.
pathways and so on and so forth. And so there's a bunch of efforts going on in various pieces of the design of RISC-V extensions in order to support this world. And we have this world-class group of people in a broad set of industries who really care about this stuff
Hmm.
and really are knowledgeable about this stuff. And they're helping us succeed in placing things into these marketplaces. And again, you're going to see in some places the same way you might have seen before in a soft CPU or something that people would replicate soft CPUs for a number of purposes.
Hmm.
You'll see them doing the same thing with RISC-V and also making real chips as well with the same kind of stuff. So at that end, the reason why, if you want to say, why is RISC-V so attractive? It's attractive for the price, the cost, and it's attractive for the freedom, the flexibility that we provide.
Right.
So we designed this product to go all the way from IoT to HPC.
Exactly.
And if you want to say, okay, so there's rocket science in a lot of pieces of RISC-V, but that flexibility piece,
Yeah.
it sometimes is looked at as like, okay, it's an attribute, but that's rocket science.
Yeah.
Trying to make something that can satisfy different marketplaces and still be coherent and not be a kitchen sink, that's attributable to the great architects that are involved. The folks who founded this stuff at Berkeley, they all contributed to this incredible success in doing this.
Yeah, that's right.
So I kind of handled this whole raft of embedded stuff in an interesting grouping. But then you go in, you say, okay, what do you do with this data? And I always find serendipity to be amazing. And so you take a look at all the guys in the 70s and 80s who were doing AI, they turned into database guys in the 90s and the early 2000s. And then they, with Hadoop and Spark and then the machine learning and a whole bunch of other things that fell out of that because you can do this distributed processing. These guys went full circle and now they've come back with NLP and everything else. But what's interesting is they're utilizing the stuff that came from HPC.
Uh-huh.
If you went to the some of the hot chip talks this past week, you'll see that the discussions around ML, AI, NLP
Uh-huh.
really had to do with MPI libraries,
Right.
the inner products and matrix and tensor stuff that you've talked about. And so I kind of love it when everything old is new again and things get revitalized. So you take folks who are traditionally HPC folks, and they are now really leading edge folks for processing this amount of data. And they're leading the charge in helping us define things like the vector extension, which we're doing an incredible job at making an incredibly flexible, incredibly targeted extension that's really intended to help a broad set of traditional applications like weather prediction and sonar and stuff. And then relatively nouveau targets like ML and so on and so forth.
Yeah, exactly.
So we're very excited about that. And that's why, if you take a look, it's the flexibility and the architectural interest and the architectural leadership of the members that are leading us to provide incredible solutions. I mean, we also saw in the hot chips, I think it was Alibaba who, and this also goes back to their previous discussion, they didn't wait till the final version of the vector spec to get vector into their stuff. And they added on top of that really adds value for their customers.
Yeah.
And we give them the flexibility to do that.
Yeah.
And so, of course, they have to go ahead and invest with the tool chain and other things to make that a success. And they will eventually merge back in as appropriate. But it's this community, it's this freedom, it's this flexibility that is fueling the use and the amazing broad set of targets.
Yeah, I saw that talk at Hot Chips, and it was very interesting and a very active Slack channel side discussion about it as well. Let's just go to AI and HPC since we're talking about it. So we can expect to see all manner of expressions of RISC-V in that market segment, right? There's quite a bit of interest in that community, as you know, to see RISC-V out there. I know Barcelona Supercomputer Center is doing some great work and associated organizations in Europe.
Yeah, the ETH.
Yeah, exactly. What is the general status of that market?
First of all, I just want to expand that interestingly enough, it's not the top end alone that's interested in ML. There's a bunch of machine learning, AI, other things that are going down into device controllers. They're making interesting decisions down the bottom, and maybe it's a subset of the things that you might find at the top. But I don't think we can think
It's a great point.
too much about boxing people into certain molds in this world. I mean, one of the great things about reusability and open source and the communities is people find interesting ways to use technology where you don't expect them to use it. So we are finding that people are looking at various AI and adjacent technologies all the way from the bottom to the top. And the folks in Europe are certainly helping us lead the charge in some of the stuff, like you said, the Barcelona Supercomputer Center. I mean, I've seen some talks by some of the folks involved with that, and they're brilliant, and it's absolutely wonderful.
They're very good. I was very impressed.
And they've set down, basically guidelines saying if you're moving forward, you have to use this, right? And that you've seen that in a number of places where people don't want to be beholden to a proprietary architecture. They don't want to be beholden to an architecture that's driven by one big partner. They want it to be something that is broadly accessible, broadly modifiable, broadly available. And so I think that you are seeing this renaissance. I mean, there's no other word for it.
That's a good word, yeah.
Look, all of computer science is heading that way over the last 15 years. How many databases, how many scripting languages, how many chips, how many this, how many that. It's all exploded because we have this base to build upon, that we have this open source philosophy to build upon, and we have a community mentality to build upon. And so it really is fueled by folks like the HPC community, and then absconded with by people in the embedded community. And
That's excellent. Yeah. Yeah. Of course, that's also leading to this whole edge computing phenomenon.
Yeah. And I will tell you, so one of the things you need to look at is that there's different runways for getting actual products out based on a new chip. So it may take, these 4 undergraduates did a chip in 4 months. Very senior people can also do a chip that's probably more sophisticated in 4 or 6 months. But they're going to put it into a product that may have a natural life cycle of a year and a half, 3 years, whatever. And so you're seeing those basic things being designed now, and then they'll end up in products over the next 2 to 5 years. And that's why you're going to see hundreds of thousands of cores show up in the world that are based on RISC-V.
Yes.
And the reason I bring this up is because the things with the shorter runways get out first.
Right.
So people are working on all the pieces all the way through, everything from, again, IoT to network edge to targeted cloud computing to finance to defense, oil and gas. All these industries, all these target uses of technology, those are all going on. But the guys at the bottom have a much more restricted set of things they need to accomplish in order to get a product out. So you're going to see those come out first. But very shortly afterwards, you see other things up the stack that also don't require general purpose computing, right? They're not going to have a random set of programmers or a random set of customers using this product. They're very targeted in a specific way, whether it be network edge or storage edge, which is another piece of that's going on, or specific cloud computing or specific HPC usage. But you're going to see the specific stuff, the targeted stuff, the reduced set of applications, the reduced set of operating system variations come out first. And then you're going to see some of the more general purpose stuff, the laptops and desk sides and, one use and honking servers and all that kind of stuff evolve over a period of time. And sometimes it's some of the same companies doing multiple things. So they learn from their targeted specific architectures and designs, and then they expand that into other marketplaces.
That's excellent. You were talking about hundreds of thousands of cores, and it reminded me that when I worked for Azul Systems, where I went to after Sun, we were building a highly multi-core, many-core chip at the time. I wrote an article in the Register saying that we should get ready to use kilo and mega as it applies to cores, just like we do applying to bytes. And I think we're finally getting to that point when people can actually talk about a mega core system.
Yeah, absolutely. And again, I go back to the Hot Chips conference this week, and you saw a number, not only in RISC-V, but in other architectures where you have an extraordinary number of cores. You have big progress in the other pieces around the cores that need to evolve in order to make that many cores useful.
Yes.
So the memory interconnect, the I/O interconnect, the inter-CPU interconnect, all the coherency algorithms, all the software that has evolved over time to make use of parallelism, all those things are coming together, and all those things have an amazing number of contributors around the world to those technologies that enable corporations to provide real product to their customers that bring real value.
I envy every one of them because those problems must be so fun to work on.
Oh, I agree. And I consider myself a technology hound. I like to read about technology. I encourage and am excited about other ISA architectures and what they're doing. I'm excited when they're excited about what we're doing.
Right.
And, in the end, a bunch of us are engineers. We talk all the time at these conferences, and we get blown away and we get inspired, and we allow our companies to make good profits and great inroads with their customers based on the collective technology of the world moving forward.
Let's talk a little bit about 5G, in part because it is so much in the news. It's become a matter of geopolitical importance and some controversy. But nevertheless, by all counts, and we've been tracking that technology, it is happening. It is happening with pretty good pace, and progress is there. And the use cases for which it is required are very important, and it's going to enable new markets, etc. Is that an area that the RISC-V community is also paying attention? I mean, you can look at like the MIMO piece of 5G, and before you know it, you're solving partial differential equations. So there's like, my God, there may even be an HPC angle there. But there's also just the processing of the data and the traditional switching and networking and the handset and all that. What does the scene look like there?
This starts going into my observation of the world as opposed to necessarily some particular observation about the RISC-V world.
Mm-hmm.
So I will say that, you and I worked at a company that said the network is the computer and the computer is the network, right?
Right on.
And it doesn't really matter whether you're talking about 5G or the next generation of Ethernet or Wi-Fi or Starlink or whatever it is. The truth is, we live in a world that behaves better when our connections work better.
Mm.
And we saw some stuff, for example, at Hot Chips that allows rack mounted servers to talk at fairly low latency speeds across the data center that
Yes.
we've never been able to do before.
Yes.
And so these worlds are merging. I work on graphite systems, which use,
Yep.
a 10 gig E in order to talk to flash devices. And so it's really, these things are happening at every level of technology. And RISC-V is showing up in all of them for the same reasons, the flexibility. So you have people doing 5G stuff and they're using RISC-V cores to do it. And you have people doing Wi-Fi and using RISC-V cores to do it. And you have people doing memory interconnects and using RISC-V cores to do it. So we're showing up everywhere where you see this interconnect technology going on. And still, things always take time to evolve. But you and I have seen more evolution in the speed and the functionality, the usage of these interconnects at all levels at such a rapid pace over the last 15 years that I'm excited by it all. I wouldn't want to say one over the other. I think they all facilitate stuff. And then over time, what we've seen is some of them overlap, right? And then we find ways to either merge or make those things interact in positive ways. So my view of the world is, look, if you take a look at the traditional Hadoop MapReduce stuff, they don't put the word shuffle in there, right? It's that data movement that is the challenge.
Absolutely, yes.
For a lot of things. It's a challenge to go to disk. It's a challenge to go across the network. It's a challenge to do it in a securely safe way, and so on and so forth. And that epitomizes, in my mind, everything from very small inside a device communications all the way through huge fiber channel interconnects and so on and so forth.
Excellent. Now, we talked about accelerators a little bit. Is there anything under that topic that you want to add? Or is that also...
Well, first of all, so accelerators are an overused term. So please explain what you mean by that.
No, it means basically what I was saying before. There are ways of just accelerating specific computations or tasks. And what I'm seeing in the market is we've gone from scalar to vector. Vector was the norm for a while, and then it kind of went away, and then it's come back now. And then with AI, we are seeing matrix processing. Again, that also existed in the old days, but it's kind of made a comeback. In fact, we can get into multidimensional matrices and do tensor processing, such as it is. And then also parallelism, that is pipeline parallelism versus actually concurrent parallelism.
Yeah.
And that's like FPGA versus GPUs and that sort of a thing.
I agree with what you just said. I wrote my first vector program in 1977 on Cray 1 number 6.
Oh, wow.
And
awesome.
It was a rank of a matrix, So like you said, things come and go, but I think good computer science doesn't go away. We keep it in our back pocket and we bring it out when we can take advantage of it. And we've done a lot of that over the last bunch of years. Mm-hmm. And we've also coupled it with what we've been doing all along, which is enhancing concurrency, enhancing SMP, making all those pieces, A, work more efficiently, and B, be translatable from developers' programs into something that actually performs, so that whole raft of stuff that occurred with Hadoop and Spark and MPI informed what we do now with some of the ML stuff and NLP stuff and so on and so forth.
Right.
So good computer scientists take what they've learned before and they make use of it and take advantage of it as we move forward to the future. So there's a lot of accelerators that are going on. Some of them are standard community-based stuff, and some of them are specific to a particular corporation, a particular application where people need stuff. But when you see multiple companies saying they want the same thing, often they get together and bring it back to RISC-V and say, hey, we're proposing that we add an extension to RISC-V that does this. And they put a charter together, they get a group together, they put a proposal together, they work on some POCs and designs, and then they move on to making an extension and moving it forward. So one interesting example is all the stuff that's going on with crypto. You and I started way back when security was an afterthought. There was no Spectre and Meltdown and side channel attacks and so on and so forth. We have some of the most sophisticated architects on earth helping us figure out what our customers need to secure their systems. Well, guess what? we can go ahead and do AES 128 like in one instruction with a vector instruction.
Oh, brilliant.
If you don't add any of our crypto stuff, it takes over 1,000, right? If you do the crypto stuff, it gets down to like 78. And if you use the vector stuff, it gets down to 1.
That's incredible.
Talk about serendipity, right?
Uh-huh.
This meeting of technologies and the use of technologies in cases like that just showcase this acceleration that you're talking about. And
Oh,
that
I
could
think
be,
that is so important. Yeah.
yeah.
And that, of course, includes things like hardware root of trust and security zones and
Oh,
things like
yeah. Yeah, we have groups working on all those pieces and have finished some of those pieces. But my point really wasn't about security, which also is a very good point for us
Yeah,
to talk
exactly.
about. My point was just that from an acceleration perspective, one piece plays into another.
Great point. That's excellent. Let's try to close with some next steps. You mentioned the RISC-V Global Forum that's coming up. Maybe you want to tell us a little bit about that. And we use this to encourage folks to consider attending because it's always, I did the RISC Summit last year and it was absolutely fabulous. And of course, this year it's all virtual, but I feel like you're doing a tour de force kind of a implementation, which is very innovative. So tell us a little bit about that and where people can go to get more info.
Yeah, we have Global Forum in September and we have the summit back in December again. But also, just like other communities, I mean, one of the things that's great about being a community is we have all the standard meetups that you might expect in a Linux or Hadoop kind of world. And they're happening every day in Korea and Israel and Russia and everywhere, right? And so there's a lot of great discussions that are going on, and those get fed into the community and help advance the community. And then on top of that, you have these bigger get-togethers where we have the best and the brightest telling us what they're doing, telling us where they're moving the state of the art with RISC-V forward as a community. And we're seeing just an incredible number of submissions of high quality papers that you're going to see the result of at these different venues. And you'll be able to get the latest and greatest about what's going on. And I think also get inspired. I mean, that's, as a community, part of our job is evangelism, right? Not just me, but every member is an evangelist for this community, just like it is for Linux. I mean, you can't talk to a kernel developer or tool chain developer inside of Linux who isn't going to be bullish on it and encouraging on it and welcoming on it. And we are growing the same way.
And there's a lot to be bullish about and excited about. So thank you so much. I could go forever, as you know, and it's always such a pleasure. I totally look forward to the next occasion when we can continue the conversation and maybe take another snapshot. Thank you so much.
Thank you, Shaheen, and everybody should stay healthy. Thank you.
I want to thank Mark again for his time and his insights into what we think will be a very important part of the information technology landscape. We think the open source approach is becoming a standard part, a necessary part almost, of the technology scene, with every piece of technology having an open source equivalent. In that sense, it is a cultural attribute of our increasingly digital world. We will continue to track the technologies that drive digital transformation and will bring you the salient points as we learn them. Thank you for your time, and until our next episode, take care and stay safe.